And now for something completely different. We're going to be looking at infrared spectroscopy and mass spec. So first let's look at the nature of light. Light is of course composed of electromagnetic radiation, which is a perpendicular oscillating electric and magnetic field. We're going to define our electromagnetic radiation using wavelength, which is the distance between the peaks, frequency, which is the number of wavelengths that pass a point in space in a unit of time. Those are probably familiar, but we're also going to be measuring it in wave numbers. And a wave number is going to have reciprocal centimeters as its units. You can calculate the wave number by 10 to the fourth divided by the wavelength. There are a couple of important relationships that you need to know. The frequency, which is this little V sign, is equal to c, the speed of light, divided by the wavelength. And the energy is equal to Planck's constant times the frequency. So the upshot of these equations means that high frequencies with large wave numbers and short wavelengths have high energy. Okay, so the high energy electromagnetic radiation has high frequency, large wave numbers, and short wavelengths. Different wavelengths have different amounts of energy, and they cause different amounts and types of excitation. So here we have a diagram. High frequency gives us short wavelengths, high frequency, and high energy. These shorter wavelengths, higher energy things, cause our gamma rays and X-rays, and they cause ionization. So they will actually remove an electron. The near UV and the visible causes electronic transitions. So this is where it goes from a 1s up to a 2s. That's an electronic transition. It's an excitation of the electron. The infrared that we'll be looking at causes molecular vibrations. So molecules will vibrate if you hit them with just the right amount of energy. And microwave has even less energy. It causes rotational motion. Lastly, radio waves are involved with nuclear spin transitions, and this is going to be our M and R, and we're going to be able to look at the actual location of our different molecules using that. That's the next chapter though, so don't worry about that now. You know, of course, that the electron transitions are quantized, but the rotation and vibration of molecules is also quantized, restricted to certain energy levels. And if we hit a molecule with just the right amount of energy, it will cause it to vibrate, and it will absorb that energy. So molecules can stretch in various ways. So we have here several modes of stretching. We have a symmetric stretch, where this stretches out and this stretches out at the same time. Just like you can envision those bonds being springs. So they're going in and out in sync. They can also go asymmetrically. So this one comes in and this one goes out. So they're asymmetrically stretching. The molecule can also have bending and scissoring, where they bend together and then they'll bend apart. They go back and forth. So when a molecule is bombarded with radiation of a frequency that exactly matches the frequency of the vibration of one of its bonds, it's going to absorb that energy. And this is what the spectrum is going to look at. And I realize it is, as we orientate ourselves here, at the bottom we have wave numbers. It's going to, over here we're going to have 4,000, and down here we've got 600. The y-axis, this is 0 transmission, and this is 100% transmission. So this thing is going to look upside down. This is a peak because it's showing absorption. The spikes here are absorption bands. What else did I want to say about these? Oh, and we can see here we have oxygen that's bound to a hydrogen. This is in an alcohol. And it vibrates at this frequency, and so we get this absorption right here because of that bond. Here we have a ketone, and it absorbs at this frequency, and so we get this band of absorption. Now these signals are going to have wave number, which just means where they are on this continuum from 600 to 4,000. They're going to have intensity. So as you can see, this ketone here has a high intensity. It absorbs almost, what are we at? About 10%. So it absorbs almost 90%. We can also have smaller intensities. This band here only absorbs about 20%. So we have wave number, we have intensity, and we also have shape. I've kind of messed this up, but you can see that this one is wide and this one is narrow. Hopefully you can still see that. And the shape is going to be characteristic of certain functional groups.